Here is a new chapter with us in the course of applied statistics. This chapter title is Discrete Probability Distributions. As the title refers, we have three words: discrete, probability, and distributions. The word discrete, we already have two types in the any variables, and we studied it before in the descriptive statistic course, that we have two types of uh, variables, discrete variables and continuous variables, where the discrete variables consist of the variables that their values have gap in between, and can be counted, separated, for example, a number of rooms in a house, a number of children in a family, a number of cars you own. This is a discrete variables, while we have another type of variables that is continuous variables. Continuous variables that refer to variables or values in a range, maybe in between lower limit and upper limit. For example, the weight of children, height of an adult, distance in between two countries. This is all are examples for continuous random variables that can be represented by um, decimal numbers or fractions. This chapter interested only in discrete values or discrete random variables, while the next chapter we will take the continuous random variables and its probability distribution. This is for the first word in the title of our chapter. The second word is the probability, and we already have studied all the meaning of probabilities and all things concerned it, like the rules for adding, rules for multiplying, conditional probability, and how we can calculate probability in any situations. And finally, the distribution probability. The distribution probability is a listing of all outcomes of an experiment and the probability associated with this outcome. And this in this chapter we interested in the probability distributions and its meaning. Before we go to the probability distributions calculations and rules and requirements, we should know the term the random variable. What is a random variable refer to? The random variable is a variable whose values are determined by chance, and we say chance because it's an important for us, not be predetermined by anyone. Only the chance that control the experiment or the trial. While we tossing a coin, we don't know what is the outcome, if it head or tail. When we rolling a die, we don't know the outcome, so the chance only determine the values in the random variable or the values in the experiment, so all the outcome of this are random variables. So what is the difference between the random variable and the probability distribution? The probability distribution refer the probability distribution logically, if we organize a set of possible values from a random variables into a probability distribution, the result will be the probability distribution. So there are a connection in between the term random variable and the probability distribution. So because if we organize a set of variables, our set of possible values from a random variable into a probability distribution, the result will be a probability distribution. So a random variable report the particular outcome of an experiment, but a probability distribution report all the outcomes as well as the corresponding probability. The tool used for the probability distributions for the discrete and continuous random variables will be discussed in this chapter and the chapter following. So, this example shows us the relation between and the difference in between their outcome and the probability distribution. There are two requirements in any probability distribution. The first requirement is the sum of the probabilities of all events in the sample space must be equal to 1. That the summation of P of X, the outcomes, is equal to 1. And the second is the probability of each event in the sample space must between 0 or 1. So if the one of the two requirements not included in any probability distribution, this will not be a real probability distribution. Should both the two requirements included. To ensure if it's a probability distribution or not, we should add up all the probability of distribution or probability of x's. If we get it 1, so the first requirement is okay, and then ensure that all the values in between 0 and 1, not less than 0 by negative number, for example, or greater than 1. It may be 0, not 0, it's the impossible event, or maybe 1. 1 is a certain event, but not greater or less than 0. Then we will step to the second section, which is the variance, mean, standard deviation, and expectation. The mean variance and the standard deviation for the probability distribution are computed differently from the mean variance for the samples. We already explained in the course of prescriptive statistics how to get the mean for a sample or population by computed by adding the values of the dividing total sum of the outcome over the small n sample size in the case of the sample mean to get an x bar. And when we want to get the population mean, which is noted by mu, we add up all the outcome in the populations and divided by capital N, which is the population mean. But we now to calculate the mean for the probability distribution, it's different. Now we have an example. Rolling a die. Find the mean number of the spots that appear when a die is tossed. Now, this is the outcome when a die is tossed from 1 up to 6, because the die has 6 numbers, and there is equally likely for all probability. So, the probability of occurring event 1 is 1 over 6, event 2 1 over 6, and so on. To calculate the mu or the mean for probability, we will applying the rule summation of x multiplied by probability of each one. So we will multiply 1 by 1 over 6 plus 2 by 2 over times 1 over 6, and so on to get the population mean for the rolling a die once. That's equal to 3.5. Let's take another example. Children in a family. In a families with 5 children, find the mean number of children who will be girls. First, it's necessary to find the probability distribution for the number of females. This example, we already take the idea of it in the previous chapter and using the tree diagram to get the outcome. When we use a tree diagram, the outcome of a children in any family where there are no only 2 outcome, female or male. Then the first trial only 2 outcome with a probability for each half. The second trial, every item will have 2 outcome. male have two outcome, male and female, and the second female have two outcome, male and female. This is the second trial, and the third trial was the same with the same steps up to the fifth trial, because the family here in the example, 5 children. The total outcome will be 2 to the power 5, which is equal to 32, because we have two outcomes, male and female, and the 5 children in the family, and use the tree diagram to get the probability in each case. We are interested in this example in finding the number of girls, so we will use this table and get the outcomes here. The first row, 0, 1, 2, 3, 4, up to 5 girls, and the probability of occurring each one. The bridge of have no girls, which is the first one here, 0 is equal 0 is equal to 1 over 32. In this case, we have from result from tree diagram that all are males, and this case not repeated only one time. So the result is 1 over 32. The probability of getting one girl occur 5 times, like in the example. Here we have female one time and 4 males, and here we have female and 4 males, and male, then female, and then 2 males, and 3 male, female, and male. And finally, all the first 4 children are male, and the final only it's a girl or female. So we count the outcomes that have only one girl. We find it 5. 1, 2, 3, 4, 5. So the when we have one girl, the probability equal to 5 over 32, and by the same steps we will get the number of girls 2, and its associated probability 10 over 32, and then when the number of girls 3, the associated probability 10 over 32. When we interested in a number of girls 4, the associated probability 5 over 32, and finally only one case that all the children are female, it's 1 over 32. Now note that the two requirements of a probability distribution are applied here. If we sum up all the probability values, we find it all equal to 32 over 32, which is equal to 1. And the second requirement, that is all the values in the range between 0 and 1. And mu equal to summation of x multiplied by p of x. We multiply each value by its associated probability and add them all up to get the population mean, which is equal to 2.5. Let's take another example. Number of trips of 5 nights or more. The probability distribution shown represents the number of trips of 5 nights or more that American adults take per year. This table consists of number of trips in the first row and the associated probability in each number in the second row. So the 6% that don't have any trips last 5 nights. If they take one trip, it's 70%. If they take 2 trips, it's 20%. If they take 3 trips, there are 3%. And finally, if they take 4 trips, they equal to 1%. So if we want to get the population mean, we will add up all the value 0 multiplied by 0.06 and plus 1 multiplied by 0.07, and add them up all to get 1.23. So this is a value for the mu or population mean equal to 1.23. Hence, the number of the trips lasting for 5 nights or more per year taken by American adults is 1.23. The second important formula for us is the formula for the variance of the distribution. If, as we studied before in the descriptive statistics course, there are two types of measures: the measures of location and the measures of dispersion. The measures of location, that's the mean, as we get it, the mean for any probability distribution. And now we study the measures, one or two measures of dispersion or variation, that are the variance and the standard deviation. As noted, the mean is a value used to summarize the discrete probability, but it doesn't describe the amount of spread in the distribution. The variance does this. The variance, we use it to study or to know how the spread and the variation in the distribution. So the variance is very important measure for us. We can calculate the variance by using this formula, that sigma square equal to summation x square times p of x minus mu square. And then we can use another measure for dispersion, which is the standard deviation, and denoted by sigma, equal to the square root for the variance. Let's use this table to simplify our calculations in any example. You can put the outcome axis in a column like this, and then put its probability distribution or probability associated probability in a column like this, and then multiplying each outcome by the associated probability here in this column, and add all them up. We will get summation here, the mu, and then find the x square for each outcome. Here, for each outcome, we will square this column and put the values here, and then multiplying this result or this column by the p of x and put the result here and sum all up. The value here minus the mu square, this is the value square, will get the sigma square or the variance of the probability distribution. Let's take an example. Rolling a die. Compute the variance and the standard deviation for the probability distribution. Recall in the example for rolling a die, we have a mu equal to 3.5. By using the previous table, we can make a column for x squared and multiplying each one by p of x and adding them all and subtracting from the mu square and get the value for the variance, which is equal to 2.917. To get the standard deviation, we can take the square root for the variance, and the value is 1.708. Hence, the standard deviation is rolling a die is 1.708. Another example, on hold for talk radio. A talk radio station has 4 telephone lines. If the host is unable to talk during a commercial or is talking to a person, the other callers are placed on hold. When all lines are in use, others who are trying to call in get a busy signal. At probability 0, 1, 2, 3, or 4, people will get through shown in the probability distribution. Find the variance and standard deviation for the distribution. And we here have the table that represent for having each outcome and the associated probability. This example refers to as a radio station that have phone lines, and maybe we call and find the line busy. So they want to know the variance and the standard deviation, maybe to take an action to increase the number of lines, but they have only 4 lines. The properties that people will get through are 0, 1 up to 4, and represented here by the p of x for each outcome. That means we will multiply each outcome by its probability and adding them all up and find mu equal to 1.95. Then we can use the previous table and get a column for squaring the x's value and then squaring x's multiplied by its associated probability 0.04 and adding all up and then subtracting we find 3.97 and subtracting minus p mu square, which we have get in the first step, which is 1.95 square equal to 2.25, and the result of the variance sigma square will be 1.262, and the standard deviation in this case is equal to the square root for the variance, which is equal to 1.123. We can get another important definition or another important terminology here in the probability distribution, which is expectation. Expectation, another concept related to the mean for the probability distribution, that is expected value or expectations. The expected value is used in various types of games, chance, insurance, and other areas and decision areas. As we noted here, the mu equal to expected value equal to summation of x multiplied by p of x. It is the same. The rule is the same for the population mean, but it sometimes we call expected value in the decision series and other situations.